So first off, thank you to all the people who have helped me out with this work over the last 4 or 5 years in various different forms and ways. So no surprise, after 2 talks, the moon has a serious weeds problem. This button, right? So yeah, lunar magnetic anomalies are all over the place. They're kind of small. They're a complete mess. For example, this is Gerasimovich anomaly. And what I like to focus on in this talk is like trying to model actually how the solar wind interacts with one of these crustal fields, meaning that I actually need to get 2 things right, meaning the ion reflection, for example, what's been observed by Artemis and what Andrew talked about, but also the surface shielding part, like how does the solar wind flow, or how does the field affect the solar wind flow, and more specifically, is there possibly a correlation with lunar swirls? So as you might know or does not know, every lunar swirl is somehow been connected with a lunar magnetic anomaly, or collocated, not necessarily connected, but the opposite does not hold. And so in literature there are more or less 3 competing formation mechanisms, and actually Mihai this morning shown that all 3 of them can work. The first one being just simple solar wind standard, that somehow these magnetic fields and the associated induced electric fields make a certain surface pattern towards the surface, probably then something which might look like the swirl. And this is what I will focus on today. 2 other mechanisms that have been recently commented and make micrometeorite impacts, which might have scorned the surface somehow and made this albedo patterns. And then thirdly, also this simple electrostatic levitation of dust and dust movement, which might somehow fall down in the right way following the magnetic fields. So as I mentioned before, if I want this to work, I need to get both the surface shielding part right as well as the ion reflection. So the one I'm focused on today is Reiner Gamma, which is a kind of a small one, but a famous one. It's been collocated with an LMA, which is, at least for our current estimates, around 500 nanoteslas. It's been reasonably approximated in the past by a few just simple dipoles, by a series of many. But I've tried to now do things a bit more accurate and actually use the observed magnetic field model. And by accurate, I mean that I need to get this fine structure of Reiner Gamma right. For example, if I take a cut here, which I stole from Andrew's paper, you see that if you go straight across it, Reiner Gamma has a few different features, meaning you have 2 bright lobes, actually very bright lobes on the outside, a slightly less bright lobe here in the middle, and then 2 dark lanes which sit in the middle, in between these bright lobes. So how I'm going to do that, I'm going to use a fully kinetic electromagnetic particle and cell code. What you need to know about this is that both the ion and the electron motion are self-consistently resolved. The code is actually completely open source if you want to play with it. Few things which are not open source are the open boundaries, which if you ever worked with codes like this, you know they're a complete mess, and probably the reason why the universe is infinite, because the guy who created, or whoever created the infinite, couldn't figure it out himself, so he just made it infinite. It really is very hard having open boundaries to work with big codes. So on top of that, I will have the observed magnetic field model, which I talk about a bit more in the next slide. And just to make things easy, I'll just work with quiet solar wind conditions, having the solar wind just flow straight down on the surface. The actual simulation domain sits here, and it's about 600 by 600 kilometers across. So this is this magnetic field model. So basically, this very, very nice Japanese guy, Tsunakawa-san, took all the 5 million Kaguya observations and lunar prospect observations, put them in some kind of beautiful magnetic model, and published this. And if you put it in a computer, this is what comes out for the Reiner Gamma region. Here is looking down on the surface, and you see here there's this very strong red. Here is where the magnetic field strength is the strongest. And if you look really, really careful, you can also see that that is kind of more or less a dipole-ish like structure if you really, really want. He has somehow corrected this for solar wind pressure in the independent magnetic field, and I'll just happily put this in the code and switch on the solar wind. So 2 things, of course, you need to keep in mind with this model is that although it's based on a ridiculous amount of observations, all these observations are made above the surface, like actually above the region where it gets interesting. So you always need to keep in mind, like, be careful, like how trustworthy are these fields actually at the surface. And then a second thing, of course, which is not included in this model is, or is not, where the model is not corrected for, is of course the induced fields by the induced electric fields by the lunar magnetic anomalies themselves. So if you switch it on, you run a simulation, this is what comes out. What I'm showing here is the ion charge density at the surface. And in blue there are a bunch of magnetic field lines which I kind of selected to kind of have this dipole structure come out more or less. And you see that Reiner Gamma kind of looks like two dipoles which are connected together. One big stronger one here and a kind of smaller one there. And just for reference, here is what comes out. You would just put an ideal dipole in the code. So at first sight, you think, oh, well, it looks kind of the same, all is peachy, this is what I want, we've figured it out. But if you look a bit more carefully, you actually see that it's not quite true. Because if you take the solar wind flux or the solar wind density as a means of characterizing how your surface albedo will look like, of course, you expect where the bright lobes are that the solar wind is more shielded so that you would have less flux or less density at the surface. And this seems to work for the inner bright lobes. Here, this dark red bit is highest shielded. But since these outer bright lobes are even more bright, you would expect that also here you will have, like on the outside, you will have shielding regions. And just looking at the solar wind density, they're not there. And then there's another problem, but that I happily transfer to the accuracy of the magnetic field model is if you look at the actual size of things, you see that the actual Reiner Gamma is way, way smaller than the magnetic field structure itself. And I think this is actually a mathematical issue with the model. Because if you put everything on the right scale, this is how it looks like. On the upper left, you see here is this the albedo pattern observed by LRO. This is what I showed before. This is the ion density, where indeed you see this beautiful shielding region here on the inside, but not the ones on the outside where you would expect them for the outer bright lobes. And they actually only show up when you start looking at the ion energy flux to the surface. Because then you see indeed that you have these three bright regions here, 1, 2, 3, which correspond to the outer bright lobes, the inner bright lobes, and then here this beautiful thing is in between, which then supposedly are the dark lanes. If you zoom this a little bit, you find that it's actually not so bad. So this is the observed albedo pattern. This is what comes out of the code. This is the proton energy flux towards the surface. And if you put this into numbers, you actually find also, just by looking at numbers, that the proton energy flux correlates best with the surface albedo. Just to kind of, well, actually, they're all good except for one. And I'm not sure why you see this here best. Okay, let's just go this one. So one ratio, so the way I characterized this is I basically took ratios between the inner bright lobes, the outer bright lobes, and then compared what LRO saw with what sits in the simulation. And all these numbers are kind of in the right ballpark, except for one, and it is the ratio between the inner bright lobe and the outer bright lobe, meaning that in my simulation, the outer bright lobes are still not bright enough. And the reason why I think this is, and this is something I'm currently working on to figure this out, is because I took a very, very easy scenario of having the solar wind going straight down on the surface, which actually is very, very tricky, because that's the most difficult case to actually reflect and deflect ions. So it's my guess that if I actually integrate over the entire orbit, meaning that I go over all the solar wind incident angles, that somehow these outer bright lobes will come out better. So why does this work? We've seen it in the previous two talks, but actually also the code shows this very well, is that this charge separation electric field really determines everything what's going on. Because the gyro radii are so big that just looking at the magnetic field, ions are just not doing anything. It's this charge separation electric field. But more interesting, and that's also interesting if you want to fly a spacecraft through there, just by observing the electric field and the magnetic field, I can actually predict from the code how the surface flux pattern will look like, and whether or not this magnetic topology will form a swirl or not, assuming, of course, that solar wind standoff would be the right mechanism. And you see that from the double here, these green, yellowish regions, they are the charge separation electric field, and they correlate very well with horizontal magnetic topologies, whereas everywhere in between, the magnetic field is more vertical, and of course does not shield that well. 2 minutes? Perfect. So one last bit is comparing now with actual flux measurements above the surface. So we've seen that the surface shielding bit works, so how about what's been reflected? Looking at the resolution of the simulation, you find actually very, very peculiar pattern. Like there are bits where actually more than 100% of the incoming solar wind is being reflected through different channels. If you want to compare it with, to say, for example, Chandrayaan, we scale this to the Chandrayaan resolution or to a resolution where Chandrayaan had reliable data, and we actually find that we find very similar maximum flux around 7%. Again, also, the simulations seem to suggest a much wider pattern of where there is reflected flux, and probably this also has to do with the fact that our magnetic field model is not so spectacular. Hopefully in the future we will also have Kaguya and maybe Artemis next to it. Good, and that's actually all what I wanted to talk about today. So we've shown that solar wind standoff kind of works. The large-scale albedo structures of Reiner Gamma we managed to reproduce. We also managed to reproduce the observed reflected fluxes. And even more, with this kind of modeling, you can actually predict whether or not an LMA may or may not form a swirl. Thank you.
All right, we've got time for a few questions.
No questions.
Any questions? Actually, I have a question. When you say standoff, typically people think about that with shocks and a magnetic field. Would you say that's the same, or would you say it's an electrical standoff?
It's an electrical standoff, yeah. Definitely not a shock.
Thank you. Anyone? All right. All right, very good. Yeah.